Okay, let's get started. Thanks. Well done to the remnant. Is this your very last lecture of this term? Ever? Might be. Yeah, okay. Sooner we get started, sooner we can finish then. Okay. Right, so just to remind you of this picture, just to again recap briefly where we finished yesterday. We'd done the single slit diffraction, we'd derived the intensity pattern, and then we were starting to look at diffraction at two-dimensional apertures, and where this is leading is that today we're going to talk, at least for about half the lecture, of how this impacts on actual practical pieces of optical equipment, so telescopes and microscopes, and then in the second half of the lecture I'm going to just spend a bit of time talking about a couple of things which are not on syllabus but just for interest's sake really, and I said that I would return to one of them in particular, which is the idea of, just to explain a little bit more about this idea of why I said waves of different colours do not interfere. So we're going to talk about that a little bit towards the end, and then we're going to finish just on introducing the ideas of temporal and spatial coherence. So, we basically finished yesterday by looking at diffraction at a two-dimensional circular aperture, and we didn't derive it, but we sort of talked about the fact that what you get if for the intensity distribution, if I take a cross-section through that picture there, is this distribution that looks, it's not a sinc squared function, but it looks a bit like one, and the first minimum happens at an angle delta theta of something like lambda over w with a factor of 1.22 in front, which just comes from the full calculation. Right. Okay. So this enables us then to start talking now about resolution of a lens, and I briefly said that the way to think about this, or an easy way to think about it, is that we can treat a real lens of width w as an infinite lens, right, which wouldn't cause any diffractive effects because this bit would be infinite, and then preceded by an aperture of width w, and so that situation gives us exactly this same angular broadening. So a lens of width w gives us, this, let's remove that box because it's just confusing, right? There we are. So a lens of diameter w gives you exactly the same diffraction pattern as an aperture with the same shape and size. Right, so that's where we were. So now we're going to talk about this in the context of basically a camera. This is what this is. So here I've got my infinite lens. That sort of light blue is supposed to be a lens of infinite extent, so itself causes no diffraction. And if that is all I had, then the light rays coming in here could focus to a perfect spot, right, an infinitesimal spot. But we're modelling a finite width lens, so we've put this aperture in front of it of width w, and so that is going to cause these diffractive effects, so we're going to get some sort of angular broadening. So here we're not going to see a perfect spot, infinitesimal spot, we're going to see some small spot of some finite size, right, and in particular of angular width this. Basically what we're doing is we're still using the Rayleigh criterion essentially that we talked about yesterday as our limiting resolution, right? If I had two sort of images, I'm saying, right, this is the angular resolution. It's going to define the smallest spot sizes I can produce, the smallest features I can resolve when I'm looking at things. It's going to determine whether I can recognize things as two separate objects or not. Okay, now in this case, so this is essentially a camera that I've drawn. This is one of the simplest pieces of optical equipment. The rays usually, often you're looking far away, so we're sort of paraxial approximation is fine. And these rays are being focused to a finite size spot, and this detector or piece of photographic film or something is one focal length away from my lens. So what does that mean in terms of actual linear size of the spot that I see on my detector or my piece of paper or whatever? Well, what we've got going on here is some sort of angular divergence, delta theta, where delta theta is given by that, and it's diverging for a distance f, the focal length, right? So that's my sort of the radius of my spot. So assuming that we're talking about small angles, I know that my R is given roughly by F delta theta, which is 1.22 lambda over WF. So that's the sort of linear size of the spot, or the radius of the spot that I expect to see. Right. Notice also that this size is dependent on both lambda, the wavelength you're working at, as well as the size of your aperture. So what you really care about is the ratio lambda over W. So for example, there are two ways to make the situation better, to get spot sizes that are smaller, which means better resolution. Two ways to do it. Either you can work at smaller wavelengths, so maybe if you're working in the visible, you want to work with blue light rather than red. Or you can try and make your apertures, your lenses, as big as possible, right? You make W as big as possible. So broadly, that's what you can do. So with telescopes, for example, where we're going next, you want to make your lenses as big as possible, as big as you dare, as big as you can afford. And then you have to live with what remains, right? So this is defining your limiting angular resolution, your limiting sizes of spots. It's going to limit your ability to determine are you seeing two things or just one. Okay. Right. So you may or may not have been thinking, okay, what if I decided to model it with the aperture the other side instead? Does that make a difference? So now it's the same diagram, but I've just put the aperture after our infinite lens rather than before. And actually, okay, assuming we're working in the thin lens approximation, the thin everything approximation, this situation is exactly the same, right? The thing that matters, as it turns out, is the parcel of rays that are actually passing through the aperture. That's the thing that actually, this width of the rays that you're allowing to pass through is the thing that defines your resolution. So actually this situation is exactly the same in terms of the diffraction effects you get as the situation before it. And the reason I'm pointing that out is because this is actually an example of where you don't strictly have plane waves anymore, because I've drawn it so that the waves are passing through the lens first, right? The lens will start to focus those rays, and then they're passing through the aperture, albeit that everything kind of here is in the same place because they're thin. But this is an example of where you don't have plane waves, but you do still get Fraunhofer diffraction. So basically the message is whenever you have some sort of finite size aperture or lens in your piece of equipment, you're going to be subject to Fraunhofer diffraction. You can even go further. I'm going to put the aperture somewhere else. I've reduced its size deliberately so that I'm still letting through the exact same parcel of rays. Right, so if you compare it to the previous diagram, I've just put my aperture here and reduce the size accordingly so that I'm letting the same rays through. You still get the same result. So the message here really is that what you want to do is build as big a lens at the front as you possibly can to let through as many rays as you can. Then you don't want to block anything after that, right? You want this front lens to be the thing that's limiting your resolution. And it leads to this result that whenever we have some kind of aperture, some kind of lens, any kind of real piece of optical equipment, we're going to have this angular spread, this Fraunhofer diffraction effect that we have to deal with. Okay, now, if you're at all uncomfortable with the idea that I was drawing situations there where I didn't have plane waves, and yet I'm still saying we got Fraunhofer diffraction. A little sort of thought experiment may or may not make you feel more comfortable, which is that you can sort of imagine you've got your aperture, okay, your rays are sort of converging towards it, and then you could imagine sort of putting in a perfect, this is supposed to be of infinite extent, so it causes no diffraction itself, right? Perfect diverging lens, quickly convert yourself into parallel rays, then put a converging lens and allow the rays to converge again. Now, both of these are supposed to be at infinite extent. Obviously, I can't draw that, right? It's a thought experiment, so you can do what you like, right? So those lenses can be infinite extent, not cause any diffraction themselves. They're thin lenses, despite what it looks like I've drawn, right? So they're all in the same place, so they're not causing any difference to the system. You're just quickly converting things into plane waves as it goes through the aperture, and then allowing it to converge as it would have. And that sort of may help you think, okay, yeah, I can see then why I'm just going to get Fraunhofer diffraction here. Right, so the key result in practical optics is that any aperture causes Fraunhofer diffraction when observed in the image plane, and you have to deal with that in your optical instruments. So I want to think about that a little bit more. Notice the brown, so things you should know, but not strictly, it's not examinable. And we're going to talk about the resolution of a telescope. Okay. So how does a telescope work? We've basically, let's look at the sort of simplest case of telescope that we looked at last term. So you've got some big objective lens, and we'll give that a width W. You've got your light coming in. We allow that to converge and sort of come out again. And then you've got an eyepiece lens here, which you then observe the rays, your virtual image at infinity. So that's your eyepiece lens. Right. So the angular resolution then is going to be defined as determined by 1.22 lambda over W, the width of your objective. Right, so you try and make your objective lens as big as you can, as I said, as big as you could afford, as big as you could dare before it gets too heavy. And that is going to then be what you then have to deal with. What you don't want to do, because I said your resolution is really being determined by the sort of the width of the parcel of rays that's coming in, you would be very, very foolhardy to then make an eyepiece lens that was, that didn't capture all of the bunch of rays, right? You need your eyepiece to be big enough that you cause no further diffraction effects after that. Otherwise, you've completely wasted your time and money in building a big objective lens. You'd never do that, right? And fortunately, it's quite easy to do that because, of course, these rays have converged. You only need to let them sort of diverge just a little way, and then you can put still quite a small eyepiece lens there, but just you need it to be big enough to capture the whole parcel. Okay. So let's just think about this a little bit more in terms of what it really means in kind of real-world applications. So, as I said, the resolution is depending here not only on the size of, your apertures, your lenses, but also on the wavelength. So when you use this in real-world applications, you need to think about the whole ratio, lambda over W. Let's think about visible light, though, first of all, and think of a very simple system, well, not simple biologically, but simple system, which is your eye, and think what is the limiting aperture size in that case, right? And it's your pupil size. That's where the light rays need to get in. So let's imagine that your pupil is as large as it can be. It's about 5 millimeters or so. You're looking at visible light. Let's say that's about 500 nanometers. And so that then gives roughly an angular resolution of about 0.1 milliradians, right? Lambda 500 nanometers over 5 millimeters. Okay. So it's probably easier to visualize what that really means by thinking of what does it mean in terms of objects you could actually resolve. So that is about equivalent to being able to resolve like car headlights, for example, about 20 kilometers away. So 20 kilometers away, assuming you've got perfect vision, assuming there's nothing in the way, assuming there's no atmospheric turbulence, you should be able to tell that a car 20 kilometers away really is a car rather than a motorbike, say, right? You can see that you've got two separate headlights. If you want to do better than that, or resolve finer features, you'd need to use a small telescope. So let's say you've got a roughly 12 centimetre amateur telescope or something. That then gives you an angular resolution about 20 times better, purely because the size of the aperture, the size of the lens, is bigger, 20 times bigger than the size of your pupil aperture. What about wavelength? So that was sort of visible light, but the fact that you've got a ratio here, lambda over W, and lambda comes into play, becomes very important. For example, when you start thinking of radio astronomy, right? You're talking about much larger wavelengths there. The largest sort of single dish telescope in the world is the Arecibo telescope in Puerto Rico, 300 meters in diameter. It is the GoldenEye in GoldenEye, the film, James Bond film. So very large. And it works at about 3 centimeter radiation. So that's its predominant wavelength that it works at. And that gives an angular resolution then of about 0.1 milliradians. So it has about the same acuity as your eye, but working at much longer wavelengths. Its top wavelength to work out is about 6 meters. There it only has 25 milliradians in resolution, so 250 times worse. Okay, so these are the things that you need to think about when you're deciding what to do, what wavelength to work out, what instrument you're going to build. What about microscopes? So they're actually quite a lot more complicated in terms of really understanding how they work. The reason is, well, okay, we don't build massive microscopes, right? We don't build microscopes with 300-meter objective lenses. And the reason is that we don't need to, because the way that you use a microscope is very different, right? So with a telescope, you're generally looking at objects very far away, whereas with a microscope, you're looking at things close up. And I'm not very good at drawing this diagram, hence why I had slides last term, but I'm going to try and draw quickly, roughly the diagram for a microscope, just to remind us. So you tend to have your objective lens, your primary lens, which has a very short focal length, as opposed to a telescope where it has a very long focal length. And you tend to put your object that you want to view roughly at the focal length. This we did do last term, right? So here my rays coming in. I'm going to do one sort of roughly at the focal length or just a little bit the other side, right? So I'm going to draw some, that's the one going through there. What am I doing? Yeah, okay, we'll draw that one parallel. And then you sort of have an objective, an eyepiece lens that you put like that so that you can view it. Those rays will all come out parallel, right? This isn't the greatest diagram in the world, sorry. Look back to your Michaelmas term lectures. It doesn't really matter for what I'm about to say. I just really want to remind you that you put the object close to the lens. It's about a focal length away. What that means is that clearly you're now starting to subtend quite large angles at the lens, right? You're no longer in the paraxial approximation as opposed to the telescope that I drew somewhere. Okay. Oh yeah, just above, yeah. So what that means is you can't just, make the small angle approximation everywhere. You have to deal with things properly with the full trigonometric functions, and that does get somewhat complicated. So probably the easiest way to just kind of do the calculation or understand the calculation is to sort of reverse it almost, just sort of think what is the smallest spot size I could produce. If we were in the paraxial approximation, if we could use that, then it would just be our normal, usual thing that we've been talking about, the 1.22 lambda f over w. But if you want to do it properly, normally we're not in the paraxial approximation, as I've just explained. So if you want to do it properly, you have to do the full treatment. This was worked out by someone called Abe, who really looked at it properly, not using any approximations. He used some kind of analogy with diffraction gratings to figure out what is the smallest resolvable feature that you could see with a microscope. And what he showed, you can find out a little bit more about Abe in textbooks like Hecht, but it's very much off syllabus here. It's quite a complex calculation. Okay, but what he showed was that the smallest feature you could resolve looked like this, where what is sine alpha? Well, there's my lens. Let's say this is my object, and alpha is that angle. So it is the angle subtended by the lens, or the half angle subtended by the lens by the object which is sitting roughly in the focal plane. Okay. So let's just look at it. So he showed that the smallest resolvable feature was given by that. So let's look at a couple of cases. Let's look at small angles, even though we've said this is generally not what we're working with, but just to show you what happens. So if I had small angles, then R equals lambda over 2 sine alpha is approximately equal to lambda over 2 alpha, which is also, of course, approximately equal to lambda over 2 tan alpha. Right, let me just label something else on here. So that distance is u, which is approximately f, because I've just said my object is sitting in my focal plane. And this is the width, this is my lens, so it has a width w. Right. So that means that tan alpha equals w over 2 over f. So R equals lambda over 2 w over 2f equals basically lambda over wf. And okay, we've lost the factor of 1.22, but you can see that that's basically what we had before, something that goes as lambda over w times f. So that was the small angle paraxial approximation, showing that you kind of retrieve the result you expect. Now if we look at large alpha, which is the situation you're usually in with a microscope, okay, well the largest we could have would mean that sine alpha is basically approximately 1, so alpha is basically 90 degrees, so your object is right close up to your lens. And in that case, what you would get is that R basically tends to lambda over 2. Okay, so that is called the Arbet limit. And it's basically saying that that's the best you can do, no matter what you do. If you're looking at something with a microscope, you can really only resolve features that are about the size of half the wavelength of the light that you're actually using. So if you want to look at smaller and smaller features, then you want to look with smaller wavelengths, basically. So if you're working in the visible, then blue light rather than red. If you really want to go much further than that, then you need to use entirely different techniques. Okay, so I've just said that that's the best you can do. Let me qualify that just a little bit more. It's not, as usual, I say something and then sort of say it's not quite true. So I'll qualify. So actually, it turns out if you do the full calculation, it's not lambda over 2 sine theta that you've really got going on. In the very general case, your spot size actually is the limiting value is lambda over 2n sine alpha, where n is the refractive index of any medium that you might choose to put between your lens and your object, right? So that thing is called, n sine alpha is called the numerical aperture. You will have come across that phrase before back in the geometric optics problem sheet where you were looking at optical fibres and things. There was something called the numerical aperture. It's basically a measure of the angular range over which your instrument can accept light, right? Because that changes if you've got some alternative refractive index other than air in your piece of apparatus. So for example, just to sort of try and make it a bit more practical, you could put a little drop of oil between your lens and your object, right? So let's say, high N oil, the highest you can do is about N of about 1.5, and so that means that R goes to about lambda over 3, right? So you can actually do a little bit better than lambda over 2 by sort of carefully choosing the medium that you can put in between the lens and the object. But that really is the limit you can do, right? So blue light, with blue light, that is about 135 nanometers that you can see the size of the features that you can actually resolve. Okay. pause for a second because I'm going to go on to something entirely different. Any questions? Okay. So, we're on the home straight, everybody. Okay. So I'm going to now spend the rest of the lecture just talking, well, apart from the last two slides, which was something different. Oh, no, sorry. My title says both interference and coherence. I am going to spend the rest of the lecture talking about these two things, right? So first of all, I'm going to look at a bit more of a proper treatment about what happens when you have light of different colours and how they interfere, do they interfere, what's really going on there. And then just the last two slides, I'm just going to talk very, very briefly, really just to introduce the idea of coherence and how it can be in two types, temporal and spatial coherence. And this, as I say, really is an introduction. If you want to know more, then I'll direct you to some textbooks. Okay. So everything that we have done in terms of looking at the two-slit experiment, the diffraction grating, to see these interference patterns, we have assumed a monochromatic light source. And so what's on this slide is really just some bullet points of some things that I have already said. So I basically said, okay, light of different colours does not interfere. And so if, let's say we're using a two-slit experiment, Young's double slit, we can shine white light on it, and what we would see is that each colour component produces its own fringes. So we'd have red fringes and blue fringes and green fringes separately. And then they overlap, and what you have is that the intensities are adding rather than the amplitudes adding. We talked about the fringe separation, so it turned out to be proportional to wavelength, so you've got red fringes with a wider separation than blue and so on. Central fringe always coincides. This is just a summary of what we know already. So I've shown this slide before as well, but this is just an example of what's going on. So here we are, let's say our white light is composed of these three colours. Here's my red fringes with the most wide separation, the blue with smaller, and what you see is this bright white central fringe, this other complex pattern of colours, and I said that it is the intensities that add. Right, so we're going to talk about, and I did promise I would say a few words about this, so we're going to talk about whether that is really true, or in what sense is it true. So, okay, now all of what I've just said is based on the bold statement that light of different colours does not interfere. Right, now, if you were suspicious of me saying that, then you'd have been right to be. Because, well, for two reasons, really. Right, first of all, what does it really mean anyway to say that a source is actually monochromatic? Let me see if I've got my laser. That's green. In fact, no light source is actually truly monochromatic, right? If I shine this laser, it looks monochromatic to us, it looks very red, but actually there will be many different spectral components of red. I mean, it's quite monochromatic, but it's certainly not perfectly monochromatic. And even if I could pick out just one particular spectral line from that red light, it still wouldn't just be a delta function, you know, in terms of frequency or wavelength. It would actually have some natural width. It would have some spread in wavelength anyway. So there is no truly monochromatic light source. So the whole argument is bogus from the start, right? And then the other thing is, like, what is interference, right? It's just addition of amplitudes. You know, if I throw a rock in a pond and I see waves spreading out, really, you know, they're going to interfere. It doesn't matter where I got my waves from, how I produce them, whether or not they have the same wavelength. It doesn't matter. Amplitudes just will add up, right? So the whole argument wasn't really right. And yet, on the other hand, I also wasn't lying to you, right? That is what you see, right? This is what you see. You do get the different coloured fringes, and it is the case that it is the intensities that add and not the amplitude. So how do we resolve those two things? So that's what we're going to talk about now. So let's just start off by looking at a picture that looks very much like our two-slit experiment that we've been considering. But I've just replaced the slits by, you know, it could be some radio antennae or something, right? Two sources of waves. And in this picture, the waves are exactly the same wavelength frequency, right? So this is a picture that looks exactly like the two-slit experiment, where I had some light source back here. I let them pass through the slits, but the wavelength and frequency of the light was the same. Okay, so this could be produced, the picture that I've got here, by just, as I say, radio antennae, just broadcasting at exactly the same frequency. So this is exactly like a two-slit, and so what I could do now, though, is change the frequency of one of the sources. Right? So now I've got something broadcasting at a slightly longer wavelength, but you still see these regions where the waves are overlapping, right? Just because one of the circles now has sets of circles now has a larger wavelength doesn't mean that I suddenly don't have these overlapping regions. I do. So they are going to interfere in some sense. Okay. So this is just a reminder of the calculation that we have done already. It's basically the two-slit calculation. What we're going to do now to understand what's happening with different wavelengths is to basically rerun a calculation we've done already, but now assume that K and omega for our two sources are actually different. But first of all, let's just remind ourselves what happened for the two-slit, where K and omega were the same for each source. So we represented our waves with complex amplitudes. We then calculated the intensity. This factor of 1/2 is just from the time average of the rapidly varying part that we spoke of. Okay, that's all I need to say there. And this is running through a calculation which we have done in laborious detail, right? So what we did for the two-slit was we assigned path lengths x1 and x2. We rewrote those path lengths in terms of the average and the difference. So x was just half x1 plus x2. Delta x was x2 minus x1, right? So we just assigned half a path difference to one wave, half a path difference to the other. We added our complex amplitudes. We took out the common term, e to the I kx minus omega t, and we were left with a cosine term. We calculated the intensity, and we got this, hopefully by now familiar to you, cos squared half k delta x type behaviour. And we were discussing that yesterday as well, right? That is the intensity distribution for an ideal two-slit. So two-beam interference in general will produce this sort of term. You can, if you want to, use the double angle formula and write it as the 1 plus cos k delta x as well. Okay, so that's standard. It's what we calculated before. I'm just reminding you of what we did in order to do it. So now what we're going to do is do the same thing, but not assume that k and omega are the same, i.e. we're going to calculate what happens for that situation. Okay, so this is what to put in the box. So my total amplitude is going to be the sum of two complex amplitudes where I'm going to write that phi 1 equals k1 x1 minus omega 1 t. So that is going to be k1 x minus delta x over 2 minus omega 1 t. And similarly, phi 2 is k2 x2 minus omega 2t, which is, oh dear, I'm going to have to do some rubbing out, x plus delta x over 2 minus omega 2t. Right. Okay, so I'm going to keep things in terms of phi 1s and phi 2s just for the minute because I don't want to keep writing out all that long stuff. And then we'll just put it in at the end. So what I want to calculate is the intensity pattern. So we'll be good and keep in the half, but we don't really need to. It's just normalization constant. Right, A times A star. So what I've got is a half e to the I phi 1 plus e to the I phi 2 times e to the minus I phi 1 plus e to the minus I phi 2. And that is going to give me half into 2 plus e to the I phi 2 minus phi 1 plus e to the minus I phi 2 minus phi 1, which is just 1 plus cos phi 2 minus phi 1. Right. Okay, so let's look at this. So that's my intensity distribution. Now, hopefully you can see that if you look back at what my definitions for phi 1 and phi 2 are, hopefully they're still up there. Yeah. Okay. You can see that if my k's and my omegas were the same for phi 1 and phi 2, right? So if k1 equaled k2 and omega 1 equaled omega 2, this would just reduce to our normal two-slit intensity distribution. So if k1 equals k2 and omega 1 equals omega 2, then out of this I would get I equals 1 plus cos k delta x, right? I'd just be left with the dependence that came from the actual path difference that these things had to travel. So if I just pop back a slide, right, what I've written there, sorry, I'll lift it up a bit, what I've written there is exactly what I've written here. Okay, but we're not in that situation, right? We've got different k's, different omegas. So let's look at what that does to the situation. So I've got, so if not, then what I've got is I equals 1 plus cos, right, here we go, this is going to be long, and this is all in brackets what I'm writing here, so k2 x plus delta x over 2 minus omega 2t, right, I'm still in the brackets of the cos, minus k1 x minus delta x over 2 plus omega 1 t. Okay, so let's simplify that a little bit. Right, so I equals 1 plus cos into half k1 plus k2 delta x plus k2 minus k1 x, again I'm still in the brackets of the cos at the moment, minus omega 2 minus omega 1 t, which I'm going to write even more simply as 1 plus cos k delta x plus delta kx minus delta omega t, where my k is going to just be my average wave number. Delta k equals the difference in, sorry, not very good at drawing k's, it turns out. Right, k2 minus k1 and delta omega equals omega 2 minus omega 1, the difference in angular frequency. Right, so that is our answer. And if we look at that, so on the next slide, I just summarise that again. That's our answer. Right, okay. And if you look at this carefully, what you've got now is some kind of interference pattern, it looks like. But look at these terms. This actually means that this is actually a travelling wave now. So before we didn't have the delta k or the delta omega term. Of course we didn't, because our wave numbers were the same and our angular frequencies were the same. But this is the general case for when they're not the same. And so you can see that this wave is going to travel across the screen. If you stay at a particular spot, it's going to oscillate at the frequency that is delta omega. And so if you go too far away from each other in wavelength or frequency, right, if omega 2 is very different to omega 1, then this is going to be a very fast travelling wave, and it just travels across the screen very fast, and you actually can't see that interference pattern. So it's there, but you only actually see it, or your detector is only sensitive to it, if delta K and delta omega are very small, so essentially monochromatic light. Now, we've just said nothing is perfectly monochromatic, okay, but light sources such as this laser can be monochromatic enough that that variation is very slow, right, so that to your eye it appears monochromatic. Right, so the message is that we will only see the interference pattern you know, if the frequencies or the wave numbers are very close together in time. Now, what I've calculated there wasn't actually quite where we wanted to get to, right? So what we were trying to show, I'm just going to flip back a few slides. What we were trying to look at was what happens if I have a single source, right? Let's say I've got a two-slit experiment. What happens if I've got a single light source, but that light source has different spectral components, right? So what we're really looking at is, let's get some coloured chalk. Let's be simple and consider just two spectral components in my light source. But what I really want is a sort of equivalent diagram to that, not to that, sorry, to that one, but with both sources. That looks white to me. It's supposed to be green, sorry. Right, but with both sources having both green and blue. So what I've calculated is not quite that. It's this picture that I'm showing on the slide. What we really wanted was that, but the calculation's a bit longer for that. So it's not too difficult, but it is longer, more than I can do in a lecture when this is sort of optional extra stuff anyway. Right, so I can just tell you the answer. The answer looks like this, if you were to throw this into an algebra program or something, or just spend a bit of paper doing it. And so you do actually, if you do the full calculation, you'd have to add up the complex amplitudes, two from here, one for blue, one for green, and then two from here, another one for blue, for green. So taking into account both the optical path difference coming from the two slits and, of course, the fact that they don't have the same wave numbers and angular frequency. When you do that, you get some term that is time varying that actually just averages to 0, and then you're left with just that term. That might not be completely obvious, but that is exactly the same result, which I shall show you now, as the result for two separate intensities. Right, so what we've got here as the result that you get out is 2 plus 2 cos k delta x cos half delta k, delta k delta x, sorry, delta k delta x. Okay, have I written that right? Yeah, okay. So we can convert the product of cosines into the sum of cosines, cos p plus q plus cos p minus q. And that means I can rewrite this as two terms, one that looks like 1 plus cos k minus a half delta k delta x, sorry, my minuses, right, delta x, and another term that looks like 1 plus cos k plus a half delta k delta x. Okay, well, if you look at my definitions of k and delta k there, this is nothing more than 1 plus cos k1 delta x as your first term, plus 1 plus cos k2 delta x is your second term, and that, therefore, is just the intensity distribution that would have come from one wavelength. That is the intensity distribution that would have come from the second wavelength. So I was right that you can just treat these as separate fringe patterns and just add the intensities. And that is just because the other bit, the time varying bit, just washes out and becomes 0 when averaged. Okay, so this is what we would see with 2 colours, for example. Just to simplify things a little bit, we would just have the intensities overlapping. You may have seen in other contexts this sort of beat pattern that you expect from 2 wavelengths. I'm just drawing an envelope. So if you have, right, so what you'd actually see if you had this situation with 2 wavelengths is some sort of beat pattern in the intensity distribution, where the fringes are sort of coming into and out of alignment, essentially. Okay. Right, so we're nearly done. Just want to very briefly finish just by introducing the idea of coherence, and specifically temporal coherence and spatial coherence. Just to give you a bit of an idea of what these terms mean, because we have been talking about needing coherent sources and things. So in everything we've done, when we were talking about the 2-slit experiment, the diffraction grating and so on, we have been assuming a particular thing, right? So if I try and redraw a picture that we used when we were looking at the diffraction grating, we sort of use this sort of picture to figure out where our positions of maximum intensity would be, right? So it sort of had, considering a wave just appearing in 1 slit and the first wavelength having got here, and the second 2 wavelengths, 3 wavelengths, and we drew a tangent and we said, okay, that's one of the directions that we'll see constructive interference. Right? Now the thing is that what that was assuming was that I've got a light source that is just producing wave after wave after wave, like there's always another wave following on that is going to produce, that is going to allow this to happen. But actually, in any real light source, you don't necessarily have that. The thing that describes that is the thing called temporal coherence. It turns out, at some point, something changes in your light source, right? And so something that does do this for a long, long time is said to have a long temporal coherence time. Turns out, if you do the full analysis, that is actually very much related to how monochromatic a light source is. So a laser, for example, it is pretty monochromatic, and it has a long temporal coherence, which is why I've been using lasers to produce these fringe patterns, because they're a very good way of doing it. But even this is not, it's not perfectly monochromatic, it's not perfectly temporally coherent. So this is the idea of, temporal coherence or good temporal coherence is needed to actually observe the fringe pattern. Spatial coherence, this is the last slide, is slightly more complex actually in terms of really how to think about it. So I direct you to this quite good book by Grant Fowles if you want to know more. It explains some things in quite a good way. But the idea of spatial coherence, we've touched upon it already actually, is that if you have some kind of extended light source, the fact that light coming from different parts of the source will not necessarily be coherent, they won't have a constant phase relationship with each other. It's quite useful even, spatial coherence. Actually, you could even use it to measure, for example, the sizes of stars just by looking at the imperfections in the interference pattern. Okay, and I'm going to stop. So that's it. Thank you very much. And have a good Easter break.